Hey Jamie, why don't you just have it grounded the square?
Yeah, well, I know a teacher who has it like taped to the desk right here. I'm like, that would drive me nuts if I was sitting there. And it's like up in his nostrils, you know, with the camera. So I'm gonna have it like hanging right here, which kind of out of the way. But it's got to be, it's a webcam.
Wait, is that
So
gonna?
it's got to be kind of close, but I'm gonna try to get it to where it.
The little projector maybe?
Sorry?
Might be messed up if you put something right there. The projector might.
Well, I'm gonna have to do a rig job, that's for sure.
That's for sure.
Yeah, I mean, I can do it out to the side. I can do it at a slight angle.
Didn't you do your electrical in your man cave or something?
Yeah.
So like, yeah.
This is nothing. No. You can run a 4-way switch. You're good.
Can't you just get a Bluetooth demo?
I don't know. I have to order what they say I can order when it comes to technology. So I have to run it through. And this webcam, hey guys, please, folks, this webcam is my option. So guys, here's tangent line approximation in a nutshell. I'm going to show you a cool way that you can actually use it. But for the most part, a tangent line approximation is going to help us find things when it's too hard to find it the way your natural tendency would say. Like for instance, if I have this square root function, which is in blue, I'm going to move this up a little bit. All right? So I have this square root function in blue. And let's just go ahead and write, well, we have it right here. There's my square root function. And it's pretty easy to use this function or just to look at this function and answer values about perfect squares. If I plug in a 0 or a 1, or 4 or 9 or 16 or 25 or whatever in there, it really is easy because we know those, right? The square root of 25 is 5, or the square root of 121 is 11. And we probably have them memorized up to a certain point, but anyway, I get nice, neat values. But what happens when I need to know what the square root of 3 is? I mean, I know that it's about 1.7, but that's not super accurate. Or what if I want to know what the, well, like the square root of 5, which is what we're going to be looking at, or the square root of 24. I don't know those values, and if I have a calculator, that's great, but if I don't have a calculator, I want to show you a way, and this is not just with square root functions, it's with anything. I can use something you already know to approximate something I don't know. Now, you have already learned how to find the equation of a line tangent to a curve, haven't you?
Yes.
So you learned that I can find an equation of like this red line tangent to the curve as long as I know two things, which are what? A point and a slope. Now, in finding tangent lines, it would be kind of hard to find the exact point 5 comma root 5, because again, I don't know what root 5 is. It's 2 point something, but I don't know exactly what that is, do I? But it's not hard to use points like 4, because that gives me 4, 2, or x values like 4, or values like 16, because that gives me the point 16, 4. So if I use points of values that I know, then I can get a really good, nice, simple coordinate for the point. We already know how to find the slope, right? How do I find the slope? We find the derivative, and if we know the little trick for the derivative, what do we do?
1 on the top, 2 on the bottom.
So double the root on the bottom, and then take the derivative of the inside part. So if I needed to find the derivative of something like this, the derivative at the point 4, 2, that would be really easy for me, wouldn't it? I could just do the math and get 2 times 2, and I'd get a slope of 1/4. If I was using this point, I could take the derivative here, right? And I would get 1/8. My point is, I can do these and find tangent lines at a lot of different spots pretty easily. Now again, I can find a tangent line anywhere. I can find a tangent line at 5 as well. But what I'm going to do, because it's hard for me, this point right here would be 5 root 5, and that root 5 is still, I'm a little puzzled by exactly what it is. If I want to evaluate something, what I'm going to do is this. I'm going to find a tangent line. And I'm going to find that tangent line as close as possible to what I'm trying to find. And if I'm trying to find root 5, which is what happens when I plug a 5 in, what I'm going to do is use the value that I'm comfortable with as close as possible as I can get to 5, which would be what? 4 or 9, and 4 is a lot closer. So I'm going to find this, because I really don't know what that value is, I'm going to use 4. And when I use 4, this is what happens. I can find the point perfectly, 4, 2. I can always find the derivative no matter what I pick, but it's really nice when I'm getting, again, a perfect value, right? A value that's not an approximation. And when I draw this tangent line in here, or find this tangent line, which I haven't found yet, right? But when I find it, look how close it is to the actual function at 5. In fact, when you're looking at that, there's hardly any separation, is there? So what I'm going to do is I'm going to, instead of trying to plug 5 into here, which puts me at a loss, right? Because I'm looking at that and going, I don't know what that value is. I don't know what the decimal is. What I'm going to do is find the equation of the tangent line, really close to that 5, and then use it to approximate the value of 5. And you would be shocked how accurate this is. So here we go. I've already said, if I plug a 5 in, I'm kind of at a loss. So what I'm going to do is I'm going to use 4, because when I plug a 4 in, it gives me an exact value, and it's really close to 5. And then I'm going to find the derivative at that same value of 4. And then here's my tangent line. Y minus the 2 equals 1/4 x minus the 4. Now, that should be something that we've already done, and we already feel comfortable doing. But what I'm going to do now is this. I'm going to use this instead of this to approximate f of 5, which is root 5. So instead of plugging 5 into this function, I'm not going to do that. I'm going to plug 5 into that function. Are you with me? And because they're so close to each other, I should be pretty accurate. Are y'all seeing that? So check it out. I'm going to come in here, and I'm just like I would have let x equal 5 there and plugged the 5 in, I'm going to let x equal 5 into the line function. So y minus 2 equals 1/4, 5 minus 4, and I'm just going to solve for y, which is what I would have been doing, right? So I end up getting 1/4 of 1, which is 1/4. I add a 2 to it, and I get 2 1/4, or 2.25. And if you're wondering how accurate that is, if I type root 5 into my calculator, I get 2.2, and I was rounding to the hundredths, I get 2.236, so roughly 2.24, which is pretty close to 2.25. And guys, I'm doing this at arguably one of the biggest parts of the curve. When you think about this thing, it really starts getting almost linear looking as you move out, right? I mean, there's a lot of curve right here, but like if I wanted to do something like root 24, I mean, root 24 is going to be way out here. It's going to almost seem, the blue line is going to almost seem flat, right? And what would you use to approximate root 24? Would I be plugging a 4 in? I could use 25, because 25, when I plug it in, gives me a 5. And that would be really, really close. And we're going to do that one next. Are you with me? Or maybe not next, but eventually. I was looking over this last night. But this is using a line to approximate a tangent line. Now, if you were to go to your calculator on an AP text and type it in there and get 2.24 and circle 2.24, you're going to miss it. Even though your answer is a better is closer to the real value, you didn't use a tangent line to approximate it. So we need to use it. If it says, find the equation of the line tangent to that and use this to approximate, or if it says, use a tangent line approximation to blah, 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 and I'm going to show you 6 or 7 different ways that they ask this question, so you'll get a little bit more comfortable. And believe me, you're going to see this at least 2 or 3 times in the AP test. Tangent line approximations, or finding the equation of a tangent line, they'll do it over and over and over again. And they can use it to find zeros, roots. There's a thing called Newton's sums, I think, or Newton's approximations, where he does the same thing, like to find out where this thing crosses, he'll do tangent lines try to get closer and closer and closer and find out where they hit the x-axis. And he'll find the root that way by doing tangent lines. We're not going to get into that in Cal 1, I guess, or APAD. But does this make sense what I'm doing here? So I'm creating a tangent line. Now, if I give you lots of hints on this one, right? But if I'm trying to find root 5, I'm really saying, okay, I'm plugging a 5 in. Dang, that doesn't work well. So if I can't do it to find, and I don't know what that approximation is, I have to think what would be the closest value to it that would help me do that, and 4 is the closest. Just like I said with the 24 I can't simplify perfectly, but 25 I can, so let's make an approximation at 25. If I said 118, find the square root of 118, what's the closest thing to the square root of 118 you know? Maybe 121, which is 11, so go with 121. All right, if I said 102, maybe try square root of 100, which is 10. So you're not going to see a ton of this, but you're going to see the tangent line approximation stuff a good bit. But I always thought this was a pretty clever way to find a radical. And I remember learning in like 7th grade, our teacher would get paid a little extra if she brought us to a math tournament. So she'd round up all the kids she thought could help her at a math tournament. And I remember her in the bus showing a way to find a square root, because back then that was a big deal. And I don't even remember the process she was using. But if I were to think now, I bet it's some variation of this without the calculus. They probably just showed you the tricks to do it. But I bet they try to find a little formula based on approximations like this. Because it's not really rocket science. All right, check out another one. What about, okay, this says find root 10 with the same process. So what would my function be? F of x equals root x. You'll never see it asked like this. They'll always give you a little bit more information. So right there, if I gave you that and said find root 10 using the tangent line approximation, is there any better value? If I plug 10, it doesn't help me, but 9 works great. So if I try 9, I get 3, so there's my point, 9, 3. How would I find the slope that I need? Take the derivative of that. So the derivative is double it on the bottom, derivative of the inside on the top, and then plug that what back in? Same 9. And then once I have my point and my slope, I have y minus the 3, 1/6, x minus the 9. So again, why am I doing this? Because this is the what? So here's my square root function, and way out here at 10, is what I'm trying to figure out. I'm trying to figure that out. But at 9, that is the tangent line at 9. And when you look at that tangent line, it is so close to the real function at 10, I'm betting it's going to give us even a more accurate answer than our other one did at 3 and 4. So check it out right here. In order, I want to plug 10 in, but I'm not getting anywhere. So I'm going to plug 10 into this. So at x equal 10 in there, y minus 3, 1/6, 10 minus 9. So you end up adding the 3 to the 1/6, because that is a 1 right there. And you get 3 and 1/6, which is 3 point, what is it, 1.16 repeated. And if I actually do find the square root of 10 to reference this, the square root of 10 actually gives me, the square root of 10 gives me 3.162, and I'm 3.166. So I'm actually accurate to the hundredths and not very far off to the thousands, just a little bit. And the further I move out on this curve, I'm probably going to be more and more accurate. Are y'all seeing this? Yeah. Okay. So anyway, but sometimes it starts looking differently.
Yeah.
Like this is an actual AP question. I don't remember what year. It's old, but it's not unusual. There are only A, B, C, D choices now. There's not a 5th choice on the AP test as it currently stands. Well, last year's was just a total weird AP test, but if it's traditional like it used to be this year, you'll have a bunch of multiple choices that'll go A through D. All right, it won't just be a couple of free response questions like it was last year. So anyway, it says for small values of h, what do you think they mean by small? I think this was poorly written. They should have said small positive values, or they should have said values approaching 0. All right, because small to me is negative a billion. That's really small. Okay, so to me that's a little off. They should have said for values approaching 0, what's the best approximation for this? Now they're basically saying, what if I had something super tiny like h equals that? How are you going to take this 4th root of 16 plus that? Well, you're like, crud, I don't have, I can pull out my calculator. I know it's going to be pretty close to what? The 4th root of 16-ish. It's going to be probably pretty close to 2. I know that, but, and you can see a lot of these pretty close to 2. I'm guessing it's not that or that. So I know it's pretty close to 2 if I'm being logical, but how would I know how to do this? It says the key to you is approximated. So what I'm going to try to think is, can I do a tangent line approximation? Now, if its value is really close to 0, what value close to 0 can I plug in there that I can simplify perfectly? 0, right? I mean really close to 0, right? So again, for small values, I would word that differently on a test if I was giving it, but I just wanted to show you what they were saying. So what I'm going to do is start off with that same kind of thinking there and think, all right, if I'm using 0, I can actually get a point right here. So f of 0 is the 4th root of 16, which is 2. I've got my point. How would I find the slope of that? Okay, so the derivative of this would be, and I don't have a little trick, actually I do, but it doesn't matter. How would you do the derivative if you were doing this? It's not worth memorizing for them. Change it to a 1/4 power and say, all right, 1/4 times 16 plus h to the negative 3/4, right? And then what happens if I plug a 0 into that? Now, does everybody know how to simplify this thing? What is the 4 on the bottom of that fraction right here that I'm pointing at? What does that mean? 4th root. So this says, keep the 1/4 out there, and then take the 4th root of 16.
Put it on the bottom.
You can, or you can say, I'm going to take the 4th root of 16, and when I'm done, then I'll deal with the negative 3. You could think like that. Or you could think, like you just said, keep the 1/4, or basically put the 4 down there on the bottom, and then take the 4th root of 16, the negative says, put it on the bottom, then cube it. So you could think of it that way, you could think of it this way. If I'm thinking of it this first way, 4th root of 16 is 2. 2 to the negative 3 is what? 2 cubed on the bottom, and you get 1/32. If you're thinking of it this way, you're saying 2 cubed is 8, 8 times 4 is 32. But either way, you're getting a slope of that. Are you with me? So point, slope, y minus the y equals 1/32 x minus the 0. So for small values of h, so for really tiny values, you would plug that really tiny value in here, wouldn't you? So what model right here approximates that? Well, it's a little ugly, but if I solved, I would get 1/32x plus 2. Well, that looks a whole lot like 1/32h plus 2 for small values of h. So when h is really tiny, you plug that in there and you get b. So it's a little odd, maybe the way they're asking it, and honestly, that's not super common, an ask like that. But do you see how it is kind of the same process? Now, most of the time it looks a little differently than this. Like, look at this next one. This is super common. I can't even remember a test that didn't have something that looked similar to this. I mean, listen, AP does some really, I'm a little bit of a nerd like this, but I kind of look forward to the release test because I'm like, okay, this is the year. I'm not missing any points. And I go in there and I take the multiple choice and I'm like, bam, print it. It's the key. And then I go back and look and it's always like one question. it's like, oh my gosh, that's the easiest question, but I didn't read it. Or maybe it's a question I've never seen. That's pretty rare at this point. But there's so much on it. Even though they put some really challenging questions, and it's interesting for me, and I kind of look forward to seeing what kind of things they do create. Probably 75% of it will be seen it 7 times, seen it 5 times, seen it 10 times. And you will really be exposed well to everything here throughout the year, and then especially when we review. So and you only need a 62% to make a 5. So most of you will do really well. Normally 3/4 of my students make 4s and 5s. And this year there's like 6 of you that I told to take BC and you didn't listen. So I can like check the box on those 5s. So we could have some massive scores in here this year as long as we don't get screwed by Corona. But we really could. My scores and my understanding that I'm seeing out of you guys is normally not this high. So it really bodes well, I think, for how we're going to look at the end of the year, which is great because last year was a little shaky. So anyway, what am I giving you here? It says f is twice differentiable, so we know that it is. If I can take a derivative twice. What does that mean? Well, no, hold on. If I can take a derivative twice, I see where you're coming with that. That just, if I can take a derivative once, it means what? It's definitely continuous, right? If it's differentiable, it's continuous. And there are no corners, cusps, any of that stuff if I can take a derivative, right? If I can take a second derivative, then what? The first derivative is differentiable, but if I can take a second derivative and I get answers, then that means I have nothing but what?
No.
A bunch of concave up, concave down, right? I don't have any cusps in the second derivative either. No vertical asymptotes in the second derivative. This is very polynomial looking to me, if it's second differentiable, okay? Now, bottom line is, what am I giving you here? The 0.21. What am I giving you here? The slope at 2 is 4. What am I giving you here? And don't just say the second derivative of 2 is 3. I'm telling you that at 2, it's positive, which is telling you that the original function must be concave up there. Good. Which may not even be important. So here we go. What is the value of the approximation of that using the line tangent to the graph? So I need to find the tangent line to approximate 1.9. Well, what's the closest thing you know to 1.9?
2.
That's 2, and I gave you all the information you need about 2, didn't I? And even some extra junk. Although I'm going to ask you a second question that's going to use that. So, which is also a really great question that a lot of people miss, but I'm going to start early this year. Okay, so I know the point. That's my point. There's my slope. So y minus the 1, the slope is 4, x minus the 2. Everybody with me? All right, because f of 2 is 1 is the 0.21, not the 0.12. Don't get that confused. All right, so all I'm going to do is I'm going to use when x is 1.9 in here, and I get y minus 1 equals 4, 1.9 minus 2, 4 times a negative 0.1, add the 1 over, so I get negative 0.4 plus 1 is 0.6. So clearly B, and I didn't need the second derivative. Now, here's my question to you, which was not asked here. Is this an under approximation or an over approximation of the actual value that would have occurred at 1.9?
Under.
Why would that be?
Because the tangent line would be going above it. Like the slope of the tangent line? What? I can't. Huh?
Anybody?
So if the graph is concave up, the tangent line will be below the concavity of the graph, so it's an under approximation.
Y'all hear that?
Yes.
Yeah, if the graph is concave up, right, if that's the actual function, right here, and it's concave up, and you have a tangent line there, and you're using the tangent line to approximate 1.9, right, because we know that at 2, right there, that would be like at x equal 2. So at x equal 1.9, it would have to be, if I'm using the tangent line, it would have to be an under approximation. Which is, I think, what you were both kind of heading towards.
I just misspoke.
It's all right.
Sweet.
Happens to the best of them.
Are y'all tracking with me? That's actually a very, it's not as common as like a tangent line approximation problem, but it'll happen once a test. It'll show up somewhere. Is this an under approximation or an over approximation? And they'll ask a question like that, and you'll have to go, oh, it's under, but you'll answer it. They say, justify your answer. We'll say, well, the real function is concave up there. So if the real function is concave up, then the tangent line would be under approximating those. Does that make sense? Anyway, you'll see that again. All right, look at number 5. Said let f be differentiable function such that f of 3 is 2, f prime of 3 is 5, if the tangent line of the graph of f at x is 3 is used to find an approximation of f, that approximation would be what? So again, I'm trying to find an approximation. Oh, to a 0. Sorry, that's what the question is. To find an approximation to a 0 of f. Now, what is a 0 again? It's where the function crosses the x-axis and makes an x-intercept, right? Or maybe it bounces, but it touches the x-axis somewhere. So I've got this random function. I don't know what it's looking like. And evidently it crosses somewhere, but I don't know how to do that. But I do know that f of 3, let's just say that, I don't know what this is, but say at f of 3, I'm up here at 2, right? And I know that the slope of 3 is 5. So I have this slope right here. We'll just say that the slope is 5. So what I'm going to do is I'm going to still use the tangent line, but this time the tangent line also is going to cross the x-axis, isn't it? And the idea here is, if it's close enough, it may not cross right where the actual graph crosses, but it's going to cross close to where the graph crosses. Okay? So same kind of thinking, except I'm not going to be plugging in a number for x and finding the y. And what number is that? If I'm looking for a 0, I'm going to be plugging 0 in for y and finding the x. Does that make sense? And stop me if it doesn't, guys. It's your, not your life, but it's your calculus life, right?
It's our education.
Right? So here we go. I know the point, I know the slope, so I can jump. I don't have to find much here. Y minus the 2, slope x minus the 3. But if I want to find the 0, again, I'm using this to find the 0 of the f function. So I'm going to plug in 0 here and solve. And I get 13, x equals 13/5, which we all know is 2 3/5 or 2.6. So 2.6 would be an approximation. Now, that might be a terrible approximation. It really might be. Do you know a really good way to find a really decent approximation if you were actually doing this method? What you do is you go in and you plug numbers in. Like if I plug a number in and I get a positive value, keep plugging in numbers until you get a negative value. So if I plug a number in, think about it. If I plug some number in and I get a positive, and then I plug some other number in and I get a negative, and it's continuous, what has to happen somewhere in between there? It has to cross the x-axis. We're actually not going to do this in this course, but it's something you do in calculus. Anyway, so right here, what I would do is keep plugging on either side until I see where they're really close together. And if they're really close together, but they're still positive and negative, I go, okay, there's got to be something right in there. So I would pick one of these numbers and do a tangent line approximation there.
Would you need the original function?
I would. Yeah, I can't do that here. But on an original function, that's what I would do, is get as close as possible. Because like, think about it. If I give you some crazy polynomial that doesn't factor, how are you going to find the zeros? Graph it on your calculator, which is great, but we haven't had graphing calculators for more than like 30 years, 35 years. Before that, what did people do? That's what they did. So you don't see this much on APCALC anymore, but back in the day, it was something that we would do to find the roots. Because we didn't have calculators that did that. Yeah?
Are all of the questions that ask you to approximate on the AB exam going to be these types of questions?
No. But a lot of them are. I mean, ultimately, almost everything we do is going to be an approximation. Because we're rounding and stuff like that. So just be, yeah, but it's something to key into. if I see approximation, I'm like, oh, wait a minute, I'm doing an approximation. They gave me a point and a slope. Huh, right? So a lot of times it will trigger that, but I think you'll get comfortable with that, George, as we move through this, and you'll see it more and more. And a lot of times they're just totally obvious, and they'll go, hey, find the tangent line, blah, 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 use it to approximate, so they'll really spell it out for you. Anyway, I don't remember if that was an AP question or not, although it's very style-like one. All right, what about this? The approximate value of this at x equals 0.12. So anybody off the top of their head know what sine of 0.12 radians is? Yeah, I don't either. I have no idea what that is. So if I'm trying to approximate that, I could use a tangent line to this ugly freaking curve that I have no idea what it looks like. But I would need to know a value that I could plug in there and get a nice clean answer. What number can you plug in there nicely that gives you a nice clean answer that I know that's also really close to 0.12? 0. So if I were to plug a 0 in here, like y of 0, 4 plus sine 0, I would get sine of 0 is 0. 0 plus 4 is 4. Square root of 4 is 2. So there's my point. I can find the slope of this. How do I find the slope of this? And how do I take the derivative of that ugly guy? Double it on the bottom. And the derivative of the inside part. What's the derivative of 4 plus sine x?
Cosine x.
0 plus cosine x. And then I'm going to take the derivative at what? Still at 0. So I get cosine of 0 over 2 square root 4 plus sine of 0, which is 1 over 2 root 4, which is 1/4. Right? So now that I have my point and my slope, y minus 2, 1/4, x minus 0, or basically y equals 1/4, sorry, y minus 2 equals 1/4 x. And at this point, I can say, all right, I can use that to find the x equal 0.12, because that I can do, right? I just have no idea what sine of 0.12 radians is. But I totally know what 1/4 of 0.12 is, and then add a 2 to it. So a fourth of that is 0.03, add a 0.03 to 2, and I get B. And for the record, if I were to square root 4 plus sine of 0.12 radians, I get 2.0297, which is awfully close to the real value. Right? Suspiciously. Are you with me?
Sure.
So in this case, even if you had pulled out your calculator somehow, although you wouldn't have it on this question, you would have actually still been right. But anyway, whatever. What about 7? For the function f, the derivative is 2x plus 1. Now, are they telling you that literally that's the slope you're going to lose using your tangent line? No, that's the formula for the slope that you're going to use to find the slope that you're using your tangent line. And they say, what is the approximation of that found by using the tangent to the graph of f? So they kind of spelled it out for you at f of 1 and 6. So they're giving you what? The point and a slope formula. So how would I find the slope at 1? Plug in the 1. So don't plug 2x plus 1 in your line. Find the slope at 1. And then y minus 6, 3x minus 1. And then say, all right, I can now say at x equal 1.1, I get 3 times 1.1 minus 1, add the 6, that's a 0.1, so that's a 0.3, and 8. It's like taking candy from a baby.
It's like taking.
Except who really want me to slobbered on candy? I never found that really fascinating.
I think it means before they started doing it.
Yeah, but when does that happen?
It's okay. It's
I
like
call
when
that
you're a kid.
tax. My kids would come home and I'm like, tax. Open it up.
Stealing is when you take
Like
your
if
own
we had some good Reese's in there, it's gonna get taxed. A little bit. Especially if it was like the pumpkins or or if they maybe got some early Christmas trees. Because there's a difference.
Or the almond joys?
Oh, I love almond joys.
No, I'm just kidding.
Actually, I like some
Almond joys are the best too.
I love
Like almond joy and even the other one. Mound.
I like Mounds.
I like some coconut. But I got coconut waters back there.
Presidential.
All right, now guys, here's an example of what I'm talking about. Check this out.
Yeah.
If I have this, and I said, hey, I want to find f of 3.1, I know that you can take 3.1 and plug it in there. And with some pain and suffering, you could actually raise it to the 5th power without a calculator. But it would be some pain and suffering, right? And if you do that, there and there, listen, all you got to do to make it uglier is make that x to the 7th, x cubed, whatever. If you did that, a lot of the time, not in this time because I checked it last night, but a lot of the time the answer you get is a choice. And it would be wrong. So literally, you sucked it up and went, oh, screw calculus. I'm doing it my way. And you plug it in there, but what you didn't do is you didn't give the approximation using a line tangent to the graph.
Oh no.
So even though you gave it a good value and you did a lot of handy algebra 1, you're not going to get credit for this. So what can I do though? It said to use approximation at 3. So I can plug a 3 in. Now I'm not suggesting that plugging a 3 in is super easy, but they did make it a little easy on you. 3 to the 5th. This is my f of 3. 2, 3 squared plus 1. Now, that's 3 cubed, right?
Yeah.
So 3 of those 3's and 3 of those 3's just leaves you a 9 there. That's a 9 times 2 is 18. So 28. So it's not too bad. They kind of took care of you by putting the 27 in there. Although if you are a former math teamer, you know that 3 to the 5th is 240. 243.
Oh wait.
Yeah, one of those. You know, we haven't even had, I give these powers quizzes. Because these, oh, you're solid, yeah, you're like, yeah, I only do it because it used to show up at math tournaments a lot, but like those might be a thing of the past. All right, guys, so check it out. There's my point. How do I find my slope?
You plug in 3.
Take the derivative. So 5/27 x to the 4th plus 4x, right? Plug a 3 in again. When I plug a 3 in again, what happens? Not really, because that's 3 3's, that's 4 3's. There's only 1 3 left, so 15 plus 12. If I've done the math right? So here we go. Here's my equation. Y minus the 28 equals 27, x minus 3. So now to do this, I am going to say at x equal 3, I am going to say 3.1. I'm going to plug a 3.1 in there. I'm going to add this 28 when I'm done, and I get a 0.1 times that, so 2.7 plus 28. And I get E. Are y'all tracking with me? All right. Merry Christmas. I believe that was your homework. But hey, guys, can I just caution you this way? I'm not going to even talk about this again until our test, probably. So if you forget to go back and look at it, you're giving up probably, I don't know, a 1/7 of your test. And it's not hard. You just got to remember what you're doing.
Have you watched season 2?
Mr. Hurry, what did you think of the debate last night?
I thought it was civil. That was the only thing I was interested in. I already know what it was fairly civil. That gave me hope in humanity, maybe a little bit. I thought looks more confident in his person.
He's a bad guy.
Like, no, I love almond joy. We're back here right now. I can send you a link that if you want to.
I think I have it.
Anything like noticeable?
No, I mean, no, nothing, no, everything is predictable.
Yeah.
There's not like, there is no surprises. Pretty much.
Up, cut that video off.